All right. Good afternoon. Welcome again to Advanced Modeling Methods. And this is lecture number 7. And as I promised, on lecture number 7, we're not going to introduce any new material. What we're basically going to do is kind of rework the same problem that we've been looking at, and with 3 techniques: the finite differencing, finite volume, and finite elements. So those 3 versions of the method of weighted residuals. We're going to do so using Matlab instead of MathCAD in a single code, so that we can actually look at this. So those of you who are not familiarized with Matlab, we can introduce some of the syntax, we can introduce some of the interface. We can look at comparing the results within the same code, which is essentially what you have to do for the assignment. It's just that the equation that you're solving is slightly different. Okay? So, are there any questions at this point for what we've covered so far? Okay. So, remember, you have 1 week from today to turn in that assignment. We're going to have lecture on Tuesday. But there's no lecture on Thursday, so you'll have the full day to work on that. You just have to submit it to me or get it to me by midnight, hard copy.
How difficult do you think it is?
Huh?
How difficult do you think the project is in terms?
It's easy for you.
Because it's easy for you.
It's hard to say, yeah. I've been doing this since I was like 2. So,
wow. That didn't even invent math back in 18.
Just
yes.
Yeah, I'm kidding, but yeah, I had started programming on a Commodore, so that was before you were all born.
It's a car. It's a car.
A car?
Yeah, the Commodore.
Is it called?
Yeah, he asked what it was. I said it's a car.
Yeah, there's the holding Commodore.
Oh, no, I don't know what that is. No, Commodore is actually pretty popular computer at the time, 1982.
Oh, geez.
Yeah, and
really bad video games on it.
you can actually play some good video games on that. Yeah. But the good thing about the Commodore 64 is, first of all, it had 64K. That was the reason why it's called 64. It wasn't a 64-bit machine. That's this century's generation of machines. Back then, we were talking about 8-bit machines. But it had 64K of RAM, which at the time was a very powerful computer. Actually, computers who control the entire air traffic control on a single airport were 64-bit machines. You got to get into a mainframe to look into performing high-level computations. 128Ks or even 1 megabyte was out of the question back in the early 80s. Actually, you would have to buy, when I had my first computer, 1982, floppies were around, floppy disks were around, but they were very expensive. So your option was a cassette tape. So you would just hook up your regular music cassette tape to your computer, and then you have to rewind, go into position, and then play, and then you'll load from there. And then you can record the same way. So you use the magnetic tape on my cassette player. It was very slow. But the cool thing about it is that it had a considerable amount of memory. And back then, hard drives were very, very expensive. At the time, you would have to pay by the meg. So 1 megabyte hard drive would be, I would say it was in the hundreds of dollars per megabyte when they became multiple megabytes. In 1994, when I got to this country, I bought my first 1 gigabyte drive, and it cost me $1,000. A 1 gigabyte hard drive. So,
He's so happy with you?
No, I don't
They're like this big too, aren't they?
No, those, yeah, they were external and they were huge. 1 gigabyte. So, but at the time, it seemed like a lot. But the good thing about what I was saying is the good thing about Commodore 64 and those old school computers at the time, there was the Atari, the Sinclair, and the Commodore 64. Epsons came later. Epsons actually took over. But those computers, the operating system wasn't in BASIC. So the operating system of the computer was in BASIC, the programming language. So you actually had to learn to program to operate your computer. It's a great thing. So you need to You needed to learn programming logic to be able to make your computer do anything. Otherwise, it will be non-functional. So it's, back then, it's a great thing. But yes, I don't know about the level of difficulty of the project. I cannot assess that. I did it. I would think that it's just a matter of, since I'm providing you with multiple options for the code, MathCAD and Matlab, it's just a matter of modifying the code appropriately. You still have to do your hand calculations, right? You have to do the derivation of the equations, especially when it comes, because the equations are going to look differently. The coefficients of the equations are going to look different because the differential equation is different, okay? The general structure, the general framework is the same. And also you have a different boundary condition, so you have to deal with that. So that's key for the project. Handling the boundary condition properly is key for this project, okay? All right, so we are going to use Matlab to implement three variations of the method of weighted residuals. And those are the collocation, local, MWR, which is, as we know, finite differencing method, the subdomain, which is also a local method, and well, it's kind of redundant to say it's local because you're breaking up into subdomains. Method of weighted residuals, which leads to the finite volume method, and the Galerkin, which is also local, method of weighted residuals, which leads to the finite element method. Now, incidentally, these are the three techniques that I require for project number 1. Okay, so this lecture today would turn out to be useful. So the problem at hand is the heat conduction problem, and we're dealing with this equation. You have the diffusion term. You have T of x, which can be either a convection term or part of the generation term. Really doesn't matter, it's just part of the equation. Plus x is equal to 0. This is the governing equation, such that x belongs to the interval from 0 to L, with boundary conditions. T at 0 is equal to T0, and T at L is equal to TL. All right? So this is about as much as I'm going to write today. Well, Matlab, are you all familiar with Matlab? Have you used it in other courses? All of you?
Yeah.
Okay, it's not my favorite. Because I think it's, in my opinion, this modest opinion, is kind of cheating. Matlab is it's like in between a mathematical spreadsheet and a high-level programming language. Most people consider Matlab to be a high-level programming language because you have to write code for it to work. The code has to be in structure format. It's procedural programming. It's not object-oriented programming. Although the newest version of Matlab, I found that you can write classes. So technically, you can do object-oriented programming at Matlab. But it's procedural code. Procedural essentially means that you can actually write functions and then call those functions. You can write your own implicit functions and call them. Technically, you can actually write structured code basically without any subdirectionality. So you don't need to use go-tos and line numbers like in the old days. So basically, you can write a structured program. And in addition to that, it offers you the possibility of performing. It has a lot of inherent functions. that allow you the possibility of performing mathematical and algebraic operations. Essentially, you can do matrix multiplication, matrix vector, you can do matrix solutions or inversions on the fly. You don't need to program your own routine to do that, or you don't need to download a subroutine that does the solution of a matrix system or algebraic system. And so it does it internally. But because of that, it has a lot of overhead. Okay? It also offers you the opportunity of plotting directly. So you can just say plot this function on this axis and it just show you a plot. So because of that, it has a lot of overhead. It has to interpret all that stuff, do a lot of stuff under the hood to be able to give you these answers on the fly. And because of that, it's very slow. You'll find today that whatever you program is very slow. So if you want to write a serious program, you don't do it in Matlab, okay? Because in a serious program, you actually need performance. You need efficiency. And we're writing 1D codes, okay? This is just completely academic. In real life, you never write a 1D code. Well, actually, I take that back because in industry, there's a lot of instances where you would need to write 1D codes when it comes to hydraulics or fluid dynamics or heat transfer. 1D solutions usually come in handy to get quick answers to something that you're trying to design or install. So 1D, yes, is useful, but for what we're trying to convey in this class, which is solution methods, method of weighted residuals, we're talking about FDM, FBM, FEM. Later we're going to talk about BEM, and we're going to talk about meshless methods. We have to think multi-dimensions, okay? We have to think 3D, we have to think geometries that are not regular. So we got to think of large scale, and real life applications are large scales. So we're not looking at n equal to 100 for the number of degrees of freedom or the number of points. We might be looking at n equal to 10 million, okay, for a real problem. So when it comes to n equal to 10 million, you need to worry about increasing the performance of your code, not only by proper programming architecture, but also by the efficiency of the compiler and the efficiency of the computer platform in which you're running. Okay, so those three things always go together. How well you write the code, okay, what is the compiler that you're using, which will optimize the assembly language in which it writes, that it writes, and the binaries that it writes, sorry. And then thirdly is where are you going to run this code, okay? And again, for us, right now, it doesn't make much difference because we write a code, and instead of the code taking 1 second, it takes 1.5 seconds. It's no big deal for us. But when you go into the hundreds of thousands or millions of degrees of freedom, that can turn into days, okay? So it is the difference between an hour and a day is now significant. So, all right, so you will find that Matlab is a very slow, if you want to call it a programming language, it is, yes, but it's very slow. So you can write a code and it will interpret it, because it doesn't compile it, it interprets what you write on the script and it provides you the solution on the fly. And it's not like MathCAD where what you write is what you see is what you get. MathCAD is a really good teaching tool. I use it for teaching because I can actually write the equations as I go and I can actually produce the results on the fly. MATLAB is not like that. You have to write a script and then you get the results. And normally the script you write, which is called an M file, is not free of bugs. So it would take you debugging and whether finding out whether the syntax is correct or not to be able to even get an answer. And you don't have as much or as many hints as you have in MathCAD to where the error can come from and so on. All right, so that's my take on things. By the way, MATLAB comes from Matrix Laboratory. This doesn't mean math laboratory, Matrix Laboratory, because the first versions of MathCAD, actually you work with a workspace, and the workspace is just the memory allocation of a matrix, and then you operate over that matrix, whatever it was it that you needed to do to that matrix. And then this has evolved into a different interface with different capabilities and so on. But actually my opinion is irrelevant in this case because MATLAB happens to be the most used or employed programming language in industry. Okay, so whatever you're going to work, more than likely you're going to end up working with MATLAB, okay, for computations. All right, so so this is what we have. By the way, some time ago, at UCF, I would say, I don't know, maybe 10 years ago, I actually recorded a series of lectures on Matlab and a series of lectures on I'm going to dig those out. I don't know where they are. It might be in UCF. They actually played them for 5 years after I used them. Some other people did for labs and things like that. So I want to dig them out and maybe put them on my YouTube site, and then you can look at them if you need some assistance on Math and Matlab. All right. So. Okay. So, this is Matlab. This is the command window, so you can make Matlab do whatever you want on this. Oh, by the way, we need
The script.
Oh yeah, the script is up, but yeah, the workspace came down here because I have larger resolution on my screen. Obviously, when I shrink it into the remote desktop, you cannot see it.
You can just click on the current folder and drag it up.
Yeah. So I already made this folder of the lectures of ME 601, the current folder, so that whatever we do, it operates whatever we save. And I've already done lecture 07M, which is a Matlab M file. And so what you can write whatever you want on this window, and assign A equal 1, and then say B is equal to A plus 3, and B is equal to 4. Okay, so it's the kind of thing that you can do here. And as pre-programmed trigonometric, transcendental functions, logarithmic functions, and as I said, matrix and vector operators. So whatever I do on the screen, I can actually do on a script, and I've already done the script for you. And this script, let's zoom this out. How do I zoom this?
I think even in the new version, they haven't updated that. They gotta go like change the editor font size.
Yeah, right.
Mm-hmm.
Okay.
Might be on there.
All right. Let me see.
Can you just control zoom?
No, it doesn't. It doesn't
No, you
work.
gotta go to preferences.
I gotta go to preferences.
On the main-
Preferences, and
on
you
the-
can change the font size to make it larger.
Okay.
Only on the main
I mean,
window, not on the script.
Can anyone not read it?
Yeah, maybe that it's not gonna show up well in the video.
Preferences to the
Oh,
right.
yeah.
Preferences
Up.
to the right.
Yeah.
Okay.
Go to fonts.
And do I do that on the command window or?
Right there at the top, fonts.
Okay.
And you can change the size to the right hand side.
Here, this one.
Drop it
Okay.
down. You can click 24.
Let's make it 24.
Cool.
Oh, that's probably too much. Make it 18 and see how it goes. Okay. All right. All right. So. All right. That's probably better. All right. So I'm not going to do this on the fly, and so we method-aware residuals. Again, we're going to do collocation, FDM. We're going to do some subdomain, FBM, and we're going to do Galerking for the same problem that we have at hand. Okay. The first instruction here, CLC, clears the command window. So we just get rid of whatever was there. So we're going to do the implementation of this 1D steady heat conduction problem. L equal 1 is the length that we're going to use. We can change this anytime and see what kind of difference does it make. Temperature on the left 15, temperature on the right 25. Okay, the number of grid points and the resolution. And the number of grid points I'm not going to hardwire to the code. I'm just going to request the user to input that. So I'm going to request the user to input how many grid points do you want. All right, and then I'm going to make dx, or the delta x, equals to L divided by n minus 1. Another nice thing about Matlab is that you don't have to worry about variable types. Okay, the fact that n is an integer and the fact that L is a real variable is irrelevant to Matlab. Matlab will determine that internally and say, well, since L is a real variable and n is an integer, I'm going to assume that's a fraction of a real number, and I'm going to make dx a real number. It does that for you. But that seamlessly irrelevant decision takes a lot of time in the computer. Okay, it takes a lot of overhead. Okay, so instead of in other high-level programming languages like C or Fortran, where you have to declare the variable before you use it, and you have to say, well, L is a float, and N is an integer, and then this division is not permitted because you're dividing a float by an integer. So you're gonna have to convert one to a float and then divide them and make that the result of float. All right. So those are the kind of things that make these easy to use, but require a lot of overhead from the computer. All right, so I am going to allocate the grid points. Now, it is important that even though I just said that you don't have to worry about variable types, you do have to worry about variable sizes, the array sizes. Okay, because if what I'm doing here is saying, well, xi, I'm going to fill out a vector that is size n by 1, that's a vector, and I'm going to fill it with zeros. Okay? By doing so, I don't care about the zeros in it because I'm going to fill it out with real numbers, but by doing so, I'm actually predetermining the size of xi, which is size n. Right? If you don't say this, you still get the right answer. Okay? Because you're going to fill it right down here. You're going to do a loop from 1 to n, and you're going to say xi, the ith element of xi is going to be I minus 1 times delta x. Okay? But by doing this, since Matlab doesn't know what xi is, and it doesn't know the size of xi, it is going to dynamically alter the size of it, which might mess up with the memory. Okay? So the first time, on the first element of the loop, okay, xi is an array of size 1. On the second element, oh, wait a minute, it's an array of size 2. So it would have trouble actually determining what the size is. As a matter of fact, if I put a comment before these, it should actually give me a warning. If I put a comment right here, yeah, it gives me a warning. See? That's going to run just fine, but it's just basically telling me, with this warning, it's not an error, it's a warning, and it's telling me, hey, wait a second, the size is changing dynamically. The variable xi appears to change size on every loop iteration. So you're prelocating this for speed. Okay? So it actually increases the speed because it already knows what size it is. All right. So this is the exact solution. And what I'm going to do is I'm going to put the exact solution into a vector of the same size. Okay, I'm not going to throw in the exact solution as a continuous distribution or a continuous array. I'm just going to say the exact solution is on those same sequence of points. I'm going to place in that vector, on that array, what the exact solution is. And this is one that we derived in class. Exact solution is a function of the cosine and the sine and x. And that's it. Same thing we did in Matlab. All right, any questions so far? The size allocation, remember, it's very important.
The t-exact is the hammered calculation we did earlier, correct?
T-exact, yes, is that function, cosine, sine, that's the exact solution to that differential equation. That's what we're going to compare against, basically. All right, so let's start with the collocation MWR, which is FDM. Again, I'm going to do the same. I'm going to allocate A and B. That's the matrix and the vector. The matrix A with the coefficients and right inside vector B. We're going to need a matrix A and a vector B for every one of the three methods, but I'm going to reuse the same. Okay, I'm going to make them zeros again, and I'm going to reuse them, just not to. I always think efficiently, because let's say we're going to make this in 3D, and n is equal now to 100,000. What's the memory allocation? It might seem small to you, but it's not. Imagine that n is 100,000. Okay, 100,000 by times 100,000. You're talking about 10 to the 10. That's 10 gigs. And each, if it's a double precision, you're talking about 8 bytes. Each of the entries is 8 bytes. So you're talking about 80 gigs. Just allocating 100,000 by 100,000 matrix. It just takes 80 gigs of the memory, of the RAM, to do that. Okay? And not all computers have 80 gigs of RAM. Right? So what does a computer do when you try to allocate something in memory that is bigger than memory?
It moves it to the hard drive.
it pages, and paging is slow, right? Even though you think your hard drive might be SATA is very fast and all that, it's not fast. It's very, very slow compared to the RAM. Okay. All right. Same thing with the B. The B is n times 1. So now let's generate the FDM system. And this is exactly the same way as we allocated the coefficients in MathCAD. Filling out the first row. The first row, well, remember it's pre-allocated with zeros. So all we need to do is allocate the ones that are non-zero on that matrix. A11 is equal to 1. B1 is equal to D0. That's basically saying that the first equation is 1 times T1, 0 times T2, 0 times T3, all the way to 0 times Tn is equal to T0. That's just going, it's an explicit equation for T, for the first T. All right? Then the actual finite differencing equations between 2 and n minus 1. Between I equal 2 to n minus 1, the coefficients will be 1 over delta x squared for the left coefficient, 1 minus 2 over delta x squared for the center coefficient, and 1 over delta x squared for the right coefficient. Okay? It's a tridiagonal system. You are going to end up with a matrix A that is tridiagonal. That is 0 everywhere, and it just have diagonal, superdiagonal, and subdiagonal filled with non-zeros throughout. However, whatever the size of it is, n can be 10 or it can be 1,000, it is going to be tridiagonal all the way through. All right, and the right-hand side vector B, which contains the generation term, which is minus xi. The equation looks like the second of t dx squared plus t plus x equals 0, so we send that x to the right-hand side, and it ends up being that. And the last element of the matrix, because we also have a first-time boundary condition, basically is A and n, the last element, the last diagonal is equal to 1, well, the right-hand side vector is equal to TL. Same thing we did.
That's the boundary condition saying the
Temperature.
temperature at the end point is going to be TL.
That's it. This is the boundary condition saying the temperature at the first point is equal to T0, and this is the boundary condition. Now, your boundary condition here is going to look the same for the project. It's going to look identical, but your boundary condition here will look completely different because you have a flux. Okay? All right. So that's it. Now, there are many ways of solving that system. A times temperature is equal to B. Now, remember, the resulting system is matrix A times the vector of temperatures is equal to B. Many ways of solving it. You can actually say TFDM is equal to the inverse of A times B. And automatically know that A is a vector. I'm sorry, a matrix, and B is a vector. So you can say this. You can technically say this inverse of A times B, and that is perfectly equivalent. But it might give you there a little warning. There it is. That's telling you, okay, this gives you the right answer, but this might be slower. Okay? Because calculating the inverse of a matrix is slower than actually solving the system of equations. Okay? So let's see what that warning says. It can be slower and less accurate. Why less accurate? This is an exact solution, right? But why less accurate? Only because of round-off. Calculating the inverse of a matrix requires more floating point operations. You're not going to see that inaccuracy in a system of 100 by 100 equations. But you can see that inaccuracy in a system of 10,000 by 10,000 equations very easily because the round-off propagates throughout the entire calculation. So this is definitely slower and it will be less accurate. So solving the system A, B is just a matter of using the backslash. Okay?
Forward backslash.
Yeah, the backslash means solve the system B over A, basically. Right? Yeah, because remember, A times T is equal to B. So who's T? T is equal to B divided by A. So by saying, this is saying B divided by A in that order. You can also say this, by the way, D divided by A. But what that would give you is the transpose of this vector. It will give you the solution, but instead of giving it to you in a column vector, it will give it to you in a row vector. Right? So then it will not have the same dimensions as x, for example. So when you go plot it, you need to plot the transpose of these. Got it? All right, so just little tricks here and there.
You may have done the forward instead of the backslash.
Oh. That's not going to give you the right solution. All right. So now we need to calculate the error of the FDM solution with respect to the exact solution. And the way I'm calculating the error here is exactly the same way you need to calculate the error on the project. On the project, I ask you to do the sum of the squares, or the sum of the differences squared. Okay? Divide that by n, where I do here. Take the square root. But I ask you to divide that by the difference of the maximum and minimum numerical value. Okay? Maximum TFDM minus minimum TFDM. In MathCAD, we divide it by TL minus T0. But this is slightly different. Because TL minus T0 is not the full span of temperatures. Remember that there's a temperature somewhere in the middle that is slightly higher than TL. All right. So there it is. And then I create a string which has a prompt. And I do that just to display to the screen. FDM error is the numerical value or of num to string is the string value of this error FDM. I just make that number a string, and since I multiply it times 100, that's a percentage, and I display it to the screen. Okay, is that clear? All right. So then I'll do the same with FBM, and actually this almost looks identical because the resulting coefficients of the FBM, we did the integrations in class and all that. The resulting coefficients are almost identical. So here where we had 1 over delta x squared, we just have 1 over 24 plus 1 over delta x squared. And the FBM. Where we had 2 over delta x squared, now we have 11 over 12 minus 2 over delta x squared. And where we had, actually, I'm sorry, we had 1 minus 2 over delta x squared, now we have 11 12 minus 2 over delta x squared. And where we had just simply 1 over delta x squared, now we have 1/24 plus 1 over delta x squared. Still symmetric, because the equation is symmetric, but it's slightly different than the FDM solution. And the first and the last equations are identical, as you can see, because it's the first kind boundary condition. Now, the equation here and the project is going to change completely, because you have to do the finite volume formulation on the first node. On the first finite, on the first subdomain, which is half the size. All right? And then these coefficients will turn out to be slightly different. We did it in class, by the way, the notes. All right, so same thing. Then solve the system, B over A. And basically sum the differences of the square of the differences, divide by n, take the square root, and then normalize that to the maximum minus minimum FBM values. And then create a string that shows that error and display it to screen. It's pretty much identical to the previous one, except the coefficients are slightly different. Any questions?
So for our project, we can use the same code and just make sure that we do our math correct.
Yeah, your project is going to have different coefficients. Okay. This is going to be the same, and this is going to be different. The coefficients are going to be different because the equation is different. Yeah. So, well, this one might be almost the same, but there's a k that's going to come up because in the project there's a k multiplying the second derivative. But this one is associated with t in this problem, and in your case you have dt dx. So this one will look slightly different. This one, you have to come up with it. All right. All right, so the Galerking, now this one is different. All right, and it's different. The implementation in Matlab is different because you do have to calculate these integrals. Okay, we could have done those integrals by hand and just come up with the coefficients ourselves. But the way I did in MathCAD is I let MathCAD do the integrals for me. Those integrals are easy because you basically calculate the integrals of quadratic functions, and that's easy to do. I just didn't want the mess of delta x's and x minus xi's and so on and so forth. So, all right, so let me show you how I did this. You can do this in many different ways. You can calculate integrals in many, many different ways in Matlab. I chose to use the symbolic integrator because these are polynomials, and symbolic integrators, polynomials are easy. So INT is the symbolic integrator in Matlab. So what I basically did is I defined the symbolic variable x. Okay, I'm not going to use it for anything but just as a symbol for integration. Okay, and x, if I highlight, it should highlight it everywhere I use it. That's not highlighting.
You hover over systems X.
Maybe it doesn't do
You
it for
highlight
symbol.
that X. Okay.
Okay. Maybe because I changed the font. I don't know. All right. So here. So remember that matrix, the matrix K, the stiffness matrix is a 2 by 2 matrix, and the elements of that stiffness matrix is what makes up the coefficients of the equation. So the coefficients of the equation, this one's right here. There they are. K21 at I minus 1, so I'm making J equal I minus 1, okay? So K2J is K21, is the element 2,1 of the stiffness matrix on the previous element, right? K22J is the element 2,2 of the stiffness matrix of the previous element. K11I is the element 1,1 of the stiffness matrix of the current element. And K12I is this 1,2 element of the stiffness matrix of the current element. And those are calculated through these integrals. And so is F2J and F1I. Again, remember, the J that I'm using is just to denote that it's I minus 1. It's on the previous element. All right? So I'm basically calculating the integral of the derivative of the trial function plus, or times the derivative of the trial, and the derivative of the trial function is 1 over delta x. Trial function number 1, and trial function number 2, trial function number 1 is minus 1 over delta x, and trial function number 2 is 1 over delta x. So the derivatives of phi. Okay? Well, this is phi 2, and this is phi 1. Okay? Where phi 2 is x minus xi divided by delta x, and phi 1 is xi minus x divided by delta x. So this is the function that I'm integrating from here to here, before the first comma. And that integral is a function of x. And notice this is a polynomial of order 1 times a polynomial of order 1, so I'm basically integrating a quadratic function. And I'm doing so symbolically, analytically. So what Matlab is going to do is going to come up with the analytical solution of this integral, which is a polynomial of order 3, and it's going to evaluate it. It's going to take that integral with respect to x, so it's going to look at this variable, and integrate it. And it's going to then evaluate this at this limit of integration, evaluate this at this limit of integration, and subtract the difference, and give you the finite integral. Okay? So it does so exactly. It takes a little longer, but it does it exactly. You can do numerical integration. You can just say integral, and give it a function, and say from here to here, and what it will do trapezoidal rule. Okay? Or it will do Romberg integration, which is adaptive trapezoidal. Or it will do quadratures. You can actually control the quadratures yourself, which is another way of integrating. It's actually the right way of numerical integrating is with the use of Gauss Quadratures. Okay? So Gaussian Quadratures, it uses Gauss Quadratures to calculate integrals. Right? So you can actually control all that. But this is the analytical method, the symbolic. So, by the way, F2 and F1 is the right-hand side. The right-hand side consists of the multiplication of, this is F2 is the second shape function. The second shape function is x minus xi over delta x times x, which is what goes on the right-hand side. That's what I'm integrating with respect to x between this limit, and gives you the answer. And with that, I make up the system of equations, A and B. Same exact way I did in math. No difference. I just wanted to be consistent with what I did in math. Any questions? Now, in your project, this is going to look different for many things, for many reasons. First of all, the first equation is not 1 equal t0, okay? Because you don't have a t0 on the first node, so you're going to have to use the finite element equation on the first node, okay? The one that relates t1, t2, and q0, right? You're going to need to use that. And these integrals right here are going to, well, you're going to have to calculate the same integrals and the same two f's, but what the integrand is going to look slightly different. Okay, this one might look the same, this one might look the same, but this one's going to look different because the equation looks different. In this case, the equation was the second derivative of t plus t. In our case, it's the second derivative of t times k plus c times dt dx. Okay, so this is associated to that c times dt dx. This section right here will be associated to that. So those you have to derive by hand, put them in the report, and then implement it in the code. All right. So that's it. Any questions?
Yeah, can't ask them right now.
Well, this is going to be posted right after we finish this class, so use it, read it, make changes, and make sure that you understand everything. And then the calculation of the error is, or the solution of the system, and calculation of the error is identical to, actually I could have put this inside a subroutine. Okay, that calculates an error between a numerical solution and an exact solution, instead of repeating the lines of code over and over and over again. So use a residual calculation. All right.
I may have missed it the day I wasn't here, but what was the starting equation that, so like how you laid out the problem for us to do on the project?
Mm-hmm.
Could you lay the problem out for this?
It's what I wrote on the paper.
Oh, okay.
That's the problem we're solving on this code.
Oh, the project?
No.
You
Yeah.
mean earlier today. Gotcha.
Yeah. What I just wrote is
Okay.
what's being solved here, which is the same thing we've been solving in Matlab since the beginning of the semester. Okay, we've done it 4 different ways. Okay. All right. So now it's time to plot solutions, and this is, well, the nice thing about Matlab, I suppose, is the ability to plot the solutions without actually having to write to a graphics library and implement the statements and so on, or just to export it. What I do in Fortran usually is just export the data, right? Write it to a file, text file, and then read that text file from Excel or from Matlab or from TechPlot or whatever we can do. All right. So I am going to plot TFDM, the finite differencing solution, against XI.
Is that an orange?
O is a circle and R is red. So I'm just going to do symbols. I'm not going to do line. So it's going to do O's, or little circles, and it's going to do it in red. Okay? This is just the, what's that? And hold on means, yeah, just put it on the same plot. Then I'm going to plot TFBM against the same collocation points, and I'm going to do squares and greens. Okay, and then I'm going to do XI against that TFM, and I'm going to do plus signs in yellow. And then I am going to do T-exact, and the default identifier, I think it's blue. Blue, and I think it's just a continuous line. Yeah. And I'm going to keep it hold on. That's it. So let's see. So when we run,
Just press F5.
I can press S5 from this window, right? Can I?
No.
Or just hit the play button.
So let's see.
Just hit.
Oh, okay. It went to the command window. All right, good. Because I wanted to show you, if I do 11 points, it does it very fast. But look at FEM, still, see? It took some time for the FEM to calculate, even though it's just 11 points. And the errors, well, as expected, the FDM has an error that's okay. FBM has an error that's smaller than this, and surprisingly, the FEM has an error that's larger than FBM. That's not typical. Okay, but because this problem is constrained, it's forced from both sides. You basically have the temperature on both sides. The error is always going to be tiny, like you can see, even with 11 points. You're not going to see that in the project because you have a flux boundary condition. So you're going to see that this one is going to have a large error compared to this one, and this one's going to be the lowest error of the three. And that's usually the case. All right. So if we do this again, so again, qualitatively it's indistinguishable. But if I do this again, and I do 101 points, and it takes long. See it?
What are the units for the graph?
I didn't put anything.
Minus
in.
10 points.
It's X. I should have put a label here.
Yeah.
X label is X, Y label is T.
So y is t.
Yeah.
And x is just.
X. X. Yeah, from 0 to L. Yeah, we're not using units. It could be meters. It could be whatever. It's just a non-dimensional problem in this case.
Imperial engine.
So again, look at the error of the FEM, even though that FEM, and by the way, the FEM result is I'm not approximating those integrals. I'm actually symbolically calculating those integrals. So this is the actual FEM solution. And notice that it's identical to the FDM error.
If you were to numerically integrate it, that would be a higher or lower?
What's that?
If you were to do like the integral?
Numerically?
Yeah.
In this case, you'll get the same error. You can try it. You can use integral instead of int, and you'll get the same error, because these integrals are very, very easy to do. As a matter of fact, let me tell you, the numerical integral of a polynomial is exact, because that's the definition of quadratures. Basically, a Gaussian quadrature, the 21-point Gaussian quadrature can integrate and all the way up to an order 21. This is an order 43 polynomial exactly. Right, that's the definition of a Gaussian quadrature. So basically, this is just a second order polynomial. The quadrature will give you an exact solution for that integral. So this number will not change if you use it. It'll just be faster. All right, and same thing. If I make it, and these are the numbers you have to report. That's the plot you have to report. And then you need to do this for
9 or 8 more iterations?
no. You need to do 11 points, 101 points, and 1,001.
Oh, so
That's it.
it's 3 different iterations, but.
Yeah.
Okay.
Three resolutions, 3 methods.
3 methods. That's what I was.
Yeah. So you can see a finite volume is consistently, not by much, okay, just a little bit, under the FDM error. FEM is taking a little while.
It's trying.
I can hear your fan.
No, that's my fan in my office. I'm using the computer in my office.
It's true.
Really?
Yeah. The
Is the
music.
sound coming from the other
It's
one?
a remote desktop.
It's from both now.
It's from both.
Yeah, I'm doing remote desktop.
Ooh.
That's pretty awesome.
Yeah, so this one is the same as this one, slightly different, but that's not typical. Okay, FEM should provide you with much more quality results than FDM, but it's just because this problem is anchored here and here. So the solution, exact solution, is known here and here. So you always get very, very good solutions, no matter what. Okay. Any questions? Yeah.
Well, as soon as after I stop playing with it, I get stuck.
All right. Well, you have 1 week up to this point. So
the question is, how many questions can you ask him before he gets ended?
no, well, maybe we should implement the penalty method.
Just the Arcos 5 minutes.
Yeah, he comes to my office
Free.
asking for 5 minutes of my time 20 times a day.
Adds up.
All right. So if there are no questions right now, I'll see you next class. But you can come to my office Monday with questions or Wednesday with questions before the deadline. All right. See you later.